Hello. First, thank you to the organizers for giving me the opportunity to give this talk and for going an extra mile to allow me to do it remotely with a recording. You can think about my talk as a kind of a community service. For reasons that cannot be named, I couldn't finish my introduction in time, and I was actually thinking to give up my slot, but then I realized that I thought that this topic is way too important to be swept between under the rug. And so here I am talking about transmission spectroscopy of extrasolar planets. I will come back to this plot a little bit later, I promise. Now let's see, let's remind ourselves what's an exoplanet. That's a planet around orbiting another star. Ideally, we will just see it, like this one. This is the first image of an exoplanet. However, very few planets are located far enough from their host stars, or host brown dwarfs, as is in this case, to allow to image them directly. If we can do that, we actually can obtain an emission spectrum, and then we can analyze those spectra just as we analyze the spectra of planets in our solar system. Well, a little bit harder than that, of course. However, so as I said, this is possible for very few planets, and there is a strong bias. Most of those are actually located very far away and are at the upper end of the planetary mass regime, between 5 and 12 Jupiter masses. Almost the entire exoplanet field was predicted back in 1952 by Otto Struve, who realized that planets can be found by monitoring their host stars for radial velocity and also by eclipses, what we call today transits. This turned out to be the most powerful methods for discovering exoplanets. So here I'm trying to remind everybody that the methods of different methods for discovering exoplanets have different types of biases. So some are sensitive, and these are transits, to planets that are located very close. Some are sensitive towards planets that are located very far away. In a way, these different methods actually can complement each other. Between radial velocities and transits, we know of more than 3,000 exoplanets. The biases, however, are not limited to the parameters, to the parametric space occupied by planets. They also have imprint on the parameters that we can determine. So from radial velocity measurements, we only measure the mass of the planet, and there is a sin I factor, uncertain factor, because we don't know the orientation of the system orbit. Transits, however, give us the size of the planet, and from the size, combining it with radial velocity measurements, we also can obtain the density. These are the first two light curves obtained 20 years ago of transiting planets. From observational point of view, this is a very simple exercise. You point your imager and you keep taking images for a few hours, hopefully bracketing well the transit. Sometimes this doesn't work quite so well, but you can see it. The depth of the transit tells us what's the radius. I actually entered this game some time ago, doing transits and occultations in the infrared. This was probably the highest significance occultation. Occultation is when the planet hides behind the star. We also call it secondary transit. This was the highest significance occultation at the time. This is a work of a then PhD student of mine. And you can see that while typical transits are 1-2% for a hot Jupiter, occultations are in the regime of millimagnitudes, and these are difficult measurements. So now that we know the mass and now that we know the radius, we can start plotting diagrams like this. The colored lines here show the loci of pure iron, pure rock, pure water planets, or planets that are dominated by hydrogen, helium, and or by purely helium atmosphere. Now we can actually do some physics for a change, not just having the mass, but actually telling something about the nature of the planet. The most interesting part of the diagram, of course, is close to the origin at the lower left. And if we zoom, you will see that there are some planets there. It's not, we are not quite at the stage of doing Earths and Venus like planets. We actually know of many planets that have the size of Earth or the size of Venus, but it's very hard to measure their masses because the radial velocity effect is tiny. So, if we go further, on one of the previous slides, actually, I had mentioned transmission spectra. Of course, the solid part of the planet covers the face of the star, and we do not see any light from there, from behind the solid part of the planet. But part of the photons that of the star can cross the atmosphere of the planet and still reach us. In other words, about 1% of the entire light that comes from the star to us is filtered through the atmosphere, and absorption lines from the species in the exoplanet atmosphere are imprinted on this part of the light. Again, observationally, this is fairly straightforward. We take sequence of spectra, except in this case we try to take a sequence of spectra of many stars, not just the target, but a reference star that allows us to monitor the atmospheric telluric variations during the observations simultaneously for both the target and the reference star. And as promised, now we come back to the same slide. If we have an absorption line at certain wavelength in the atmosphere of the planet, more light from the star will be absorbed, lost to us at that wavelength. Therefore, the planet will look bigger at the wavelengths near that within that absorption line than for wavelengths outside of the absorption line. And here is a typical case. There are two sodium and potassium lines that have been observed in many planets. And we actually, if we look at within the light in those lines, the planet appears bigger. This is from our group. Girizakis, PhD student at ISU now. These are normal looking spectra of transmission spectra of four exoplanets. In two cases we actually do see sodium, and in two others we do not see. Keep in mind that the star itself has some sodium, and this is a difficult differential measurement because the exoplanet sodium is imprinted on the top of the stellar sodium. However, what if there are clouds? If there are clouds, essentially a large fraction of the light that would have filtered through the atmosphere would not do that. And that is a critical problem for this kind of studies, because most of the absorption happens at low altitude, where the density of the atmosphere is the highest. And the clouds actually prevent the light through passing through these low altitude layers of the atmosphere. The observations have shown that about in half of the cases, half of the exoplanets do have clouds. We don't have enough monitoring to know whether this is frequent, transient, they come and go, or they stay. We don't know enough about the climate these are exoplanets to tell how permanent this is, but this is potentially a problem. The obvious solution is to go to the infrared, and that's what most people have been doing so far, including us. But we can try to be clever and to turn foe into friend. Let's go back now a little bit to the to the observational setup. So we take spectra of the target and we take spectra of the reference stars. We do ratio them, and then we end up with light curves. On the left we have light curves in white light. In the right we have light curves for individual wavelength bands, and for each of those we measure the depth and therefore the size of the planet, and we end up with, voila, this kind of spectra. So this spectra, you can see some an absorption line here, you can see sodium, potassium, some water features here, etc., etc. The dots are measurements. In the context of BlueMUSE, what is the most interesting is the ultraviolet UV part of the spectra. We see a slope, and that slope has to do with the scattering from various particles, aerosol or haze, in the atmosphere of the planet. If we measure this slope, we can constrain the distribution, the size distribution of these particles. Sorry. Here are a few more spectra just to see that there is a wide variety of exoplanet atmospheres. Once we have this kind of measurements, but this field is very essentially in infancy, we can actually measure the metallicity. But why should we go into an instrument like MUSE in this for this game? And it has to do with the fact that it's an IFU. IFU instruments, by definition, have no slit losses. Slit spectrographs are subjected to slit losses. And what is worse, these slit losses are variable with time because the seeing varies, the air mass changes, stars have different colors and are subject to different atmospheric refraction. So far, there is only one paper, and that has been done with KMOS, that's doing transmission spectroscopy with the ESO IFU. And unfortunately, that paper has failed. It came up with a very optimistic estimate, but unfortunately, it failed in a sense that the star that was observed was a nearby high proper motion M dwarf, and it just drifted away. So the astrometry was not quite current, and the slit losses from the small IFU size had a major effect on the data. The KMOS IFUs are below 3 arc seconds on the side. So now there are a few things that I would like you to take away from my talk. First, that the UV observations are important because they actually can tell us something about the atmosphere of the exoplanets, and that is the distribution of the scattering particles that are present in at least half of the planets. Second, BlueMUSE and MUSE and other IFUs do not suffer slit losses, which are a major source of systematic uncertainties. Third, BlueMUSE, as we saw already, is going to be much more efficient than FORCE and also better than US. MUSE do not have an LADC, and this is important because at the level of signal to noises at which this kind of measurements are done, and we are talking about signal to noises of order of many hundreds and thousands, the systematic effects dominate the error budget, and the LADC is a moving component, optical component, and it introduces systematic errors every time we repoint the telescope or we even slightly move the telescope. There are also some potential problems. The major potential problem has to do with the limited field of view. The transiting planets are easier to find around bright stars, and this has been happening so far. The light curves for the first transit are for a star that has about 7.6, if the memory serves me right, visual magnitude. There are not too many stars like that on the sky. And for a 1-by-1 filter view, only a few percent of the exoplanet hosts have a suitable reference star nearby, and those are usually white equal mass binaries. But there are not that many that meet these constraints. However, with 2-by-2, this starts to change favorably, and even though it's not as white as the force field view, it still helps a lot. And so, if not to mention that within the Milky Way plane, this is much better and much easier. So there are plenty of targets still out of these 3,000-4,000 transiting planets. Potential source of systematics is the fact that BlueMUSE and BlueMUSE have multiple spectrographs, but one can be clever in assigning in placing the target on the filter view. There is still a moving part, the rotator, that is still there and cannot be, nothing can be done about it, except maybe turn it off. But that leads to other kind of problems, so it may not be so as wise. It has to be tried. And finally, MUSE suffered some temperature problems that hopefully will be removed from BlueMUSE if it comes to that. I have put in the PDF some links to valuable resources just for archival purposes. And at the end, I finish with paid advertisement from my sponsor. You can look at the wonderful ISO pipelines that are offered on our webpage, and the link can be seen here. And also, you can go into the Science Archive, where you will find advanced science products. That includes reduced three-dimensional MUSE cubes that you can download and extract spectra at will without having to have minor supercomputer center in your backyard to actually process the data. I'll leave this on, and I thank the hosts again.